Hello, everyone. Welcome to this lecture series. And in this lecture series, we are looking at axially loaded strengths and members. We have already looked at part 1 of axial loads. Today we are looking at part 2 of axial load. And in this session, we are going to basically look at the Poisson's ratio, the volumetric strain. We also look at work modulus, displacement in strength, strain energy of axial loaded members. So straightforward, let's start with Poisson's ratio. Good. For slender members, like what we have on the screen, let's take it that this is a slender member. And this member, the force, an axial load or an axial force had been applied through the x-axis of the member. Don't forget that here we have 3 axes. We have x-axis, the y-axis, and the z-axis. But we have a load applied only along the x-axis. And from there, we can say that because the force or an axial load has been applied along the x-axis only, there will be stress along the x-axis. And our stress, just as we know already, our stress in the x-axis is going to be the force applied over the area. However, we see from here that we don't have any force applied in the y-axis, and there is also no force applied in the z-axis. It therefore means that the stress on the y-axis and the stress on the z-axis is going to be 0. It's going to be 0. Since we have stress in the x-axis, then it means that because the force is applied along that direction, and looking at the direction of our force, this force is going to elongate the member. Therefore, we can be able to get deformation along the x-axis. And once we have deformation for our x-axis, then we can say that the strain on the x-axis, which is the deformation over the original length, or which is also the same as the stress in the x-axis over the modulus of elasticity, is going to be equal to this equation. However, we cannot say that because the stress on the y-axis is 0 and the stress on the z-axis is also equal to 0, there wouldn't be any deformation along the x-axis, along the y-axis, and along the z-axis. Let's take it that the material involved here is isotropic, which means that the deformation does not depend on the direction of loading. And what is going to happen is that because this force in the x-axis is trying to elongate the member, it will force the distances on the y-axis and the distance on the z-axis will be contracted. So when you look at this second diagram here, you find out that After the elongation, what we have indicated with the dotted lines is the initial structure. As a result of the deformation in the x-axis, it has caused the length on the y-axis to reduce. This was the initial one. But now look at the length on the y-axis. There has been a contraction because of the elongation in the x-axis. Also, so this is in the z-axis. Also, in the y-axis, you will see that this was the original length in the y-axis. But because of the deformation along the x-axis, that distance had also been contracted, and now this is the length on the y-axis. So we can see that the elongation in the x-axis has resulted in the contraction in the length on the y-axis and also in the length on the z-axis. And the measure of this contraction in the x-axis as well as the contraction in the y-axis relative to the elongation in the x-axis is what we refer to as Poisson's ratio. So as you can see from the screen, we are saying that in this case, the x and the y-axis are going to be our lateral axis. So therefore, the contraction in the lateral axis, which is both in the y-axis and the z-axis, over the elongation in the x-axis, where the force has been applied, is what will give us the Poisson's ratio. It's what is referred to as the Poisson's ratio. From this equation, you are seeing that we have negative sign there. And so the negative sign there is because there is a reduction in the y-axis. There's a contraction in the y-axis and also a contraction in the z-axis. And so that is why you are seeing the minus sign there. So it therefore means that the Poisson's ratio is just the lateral strain over the axial strain, which means that the elongation, the contraction in one axis compared to elongation in the other axis, which is loaded. And that is what we mean by the Poisson's ratio. Let's try and see what we have on our next page. Let's solve an example on what we have done. Good. So here we are told that a 500 millimeter long, 16 millimeter diameter rod made of a homogeneous isotropic material is observed to increase in length by 300 and to decrease in diameter by 2.4 when subjected to an axial 12 kilonewton load. Determine the modulus of elasticity and the Poisson's ratio. So here we are asked to determine the modulus of elasticity as well as the Poisson's ratio. And we know that the modulus of elasticity is related to the stress by this formula. The stress on the x-axis here, the force has been applied in the x-axis. So we can say that the stress in the x-axis will be equal to the modulus of elasticity times the strain in the x-axis. But in the question, we were not given the stress, and then we're also not given the strain. Therefore, if we can be able to calculate the stress and the strain, then from here we can determine our modulus of elasticity, which is E, because the stress in the x-axis over our strain in the x-axis. And we know that the stress in the x-axis is just the force over the area. It's just the force over the area. And we know that the strain in the x-axis is also the deformation along the s-axis, delta in the x-axis over the original length of the material. Then from here, we can determine our modulus of elasticity. So from here, for the Poisson's ratio, we know that the Poisson's ratio V is equal to the lateral strain. In this case, the object is cylindrical. So it means that the distance on the z-axis and the distance in the y-axis are going to be the same. So which is our lateral strain. So we can take our diameter to be in the x-axis or in the y-axis to give us the same thing. So our Poisson ratio is going to be negative epsilon y, which is the strain in the y-axis over the strain in the x-axis. So having been able to see these formulas, quickly let's run through this question and see how we are going to analyze the problem. Good. So from here, we are saying that first of all, if you want to get the stress is the force over the area, which is indicated on our screen. Therefore, we need to determine the area, and we know that the area of a circle is pi r squared or pi d squared on 4. And in the question, we have been given the diameter as 16. So it means that now our radius, if we decide to use this formula, then our radius is going to be d over 2, which is going to be 16 over 2. And that is going to give us 8. And that is what we have here. And we change to meters. And this is going to be our overall area. And in the question, we were told the force which is applied to the x-axis. The force was 12 kilonewtons. And so we are going to get 12 times 10 to the power 3. And over the area, we are going to get our corresponding stress. Then we said that once you have determined the stress, we can also determine the strain. And from there, we can find the modulus of elasticity using this formula here, which is the stress over the strain, which is referred to as the Hooke's law. So from here, we know that the strain is the deformation. Here, the force is only applied in the x. So the strain is going to be the deformation in the x-axis, which we are told that is 300 micrometer, and the original length we are told that it was 500 millimeters. So from here, which was 0.5 meters. So from here, we can just change everything there to meters or millimeters. The micrometer there is, so we have 300 times 10 to the power negative 6 meters over 500, which is also 0.5 meters. I believe that was what was given in the question. Yes. And from there, we can be able to get our strain. But when you punch on the calculator, you find out that what you are getting is a bit different from this. It's just because this has been, we have decided to express this in the engineering format. We have decided to express this in the engineering format. And from here, we can just put our modulus of elasticity is equal to the stress over the strain. And we have the stress already, and we also have our strain. So from there, we can get our modulus of elasticity. And then in the second question, we're told to determine the Poisson's ratio. And we have already stated that the Poisson's ratio is a strain in the lateral axis over the strain in the axis where the force has been applied. So in this case, the strain in the y-axis is going to be the change in diameter, in the y-axis over the original diameter. And we are given that change to be 2.4, and micro is times 10 to the power negative 6 over 16 millimeters. So we change the millimeters to also to meters. So we are going to get minus 2.4 times 10 to the power negative 6 over, we change 16 to meters, which also give us 0.0 And from there, we can get our lateral strain. Once you have gotten our lateral strain, we also have our strain in the x-axis. We just put them in this formula as indicated on the screen, and we are done solving our question. So that was quite very easy to go through and understand. So let us go to our next page and also look at the generalized Hooke law. The generalized Hooke's law. We know that up to the proportional limits, when we do the tensile testing, up to the proportional limit, the stress is proportional to the strain. And from here, we can say that the strain is equivalent to the stress over the modulus of elasticity. Now, let's consider a body which is three-dimensional, which means that we have the x, the y, and the z axis. And this body is loaded in all directions. So it means that a force has been applied on the x-axis, forces are applied in the y-axis, forces has been applied on the z-axis. So we have forces applied in all the directions along this key. So we have force in x, force in y, force in z. Therefore, it means that we will have a stress in the x-axis, we are going to have stresses in the y-axis, and then we are also going to get stresses in the z-axis, and they will not be equal to zero. They will not be equal to zero. So from there, because we have stresses in all the three directions, we are going to get corresponding strains in all the three different directions. So stress in the x, strain in the x, strain in the y, and then strain in the z. Because forces are applied in all directions, there will be stresses and strain. However, from our previous slide, we saw that the force was applied in one direction, but we stated that because the force is applied in only one direction does not mean that we are not going to get strains in the other direction. And we stated that the strain is related to the stress by the Poissons. The strain in the lateral axis is related to the strain in the axial axis by the Poisson's ratio. So from here, we can see that on the x-axis, the stress or the strain in the x-axis from the Hooke's law, the strain in the x-axis is going to be the stress in the x-axis over the modulus of elasticity A. In the same way, this stress here is going to be the principal stress from the principal strain as a result of this stress here on the x-axis. To be as a result, the whole of this strain is going to be as a result of the stress in the x-axis. But we have already indicated that if even this stress was not in the x-axis, because of these stresses in the y and the stresses in the z, there were going to be some deformations in the x-axis. And those deformations in the x-axis as a result of the stress in the y, the stress in the z, will be related by the Poisson's ratio. So we could have stated that from the Poisson's ratio, V is equal to, in this case, if there's no stress in the x-axis, then it is going to be our lateral. So we can call this the strain in the x over the stress in the, let's take it, the first one to be y. And we know that the strain in the y is going to be the stress in the y over the modulus of elasticity. So from here, then will be equal to negative of the strain in the x-axis over the stress in the y over the modulus of elasticity. And from here, we can see that the strain in the x-axis would have been equal to V multiplied by the stress in the y over the modulus of elasticity. This is going to be the strain in the x-axis as a result of the stress in the y-axis. In similar way, the stress in the z-axis is going to give a strain in the x-axis. So this is going to be negative. So let me put the negative at this side. So in the same way, the stress in the z-axis as a result of the strain in the z-axis as a result of the stress in the z-axis is going to be negative V times the stress in the z over the modulus of elasticity. So these two stresses in the y-axis and in the z-axis, we're going to produce this kind of strain in the, sorry, this is supposed to be x. We're going to give this kind of strains in the x-axis. Therefore, if we want to get the total strain in the x-axis, it should be a sum of the strain which is caused by this principal stress in the x-axis plus the strain, the lateral strain which will be caused by this stress in the y-axis, and the strain which will be caused by the stress in the z-axis. So from there, our total strain in the x-axis is going to be this strain, which is as a result of the principal, which is as a result of the principal strain in the principal strain as a result of the stress in the x-axis, and then the strain as a result of the stress in the y-axis, and the strain as a result in the z-axis. And when we put all these three together, we are going to get this as our total strain on the x-axis. And similarly, when we are considering the strain in the y-axis, we are going to get the strain as a result of the stress in the y-axis the stress in the y-axis minus the strain as a result of the stress in the x-axis, and then the strain as a result of the stress in the z-axis. And that will be similar for the strain in the z-axis. That will be similar to the strain in the z-axis. Good. So this is what we refer to as the generalized Hooke's law with respect to the deformations as a result of the various stresses in the x, y, and then on the z axis. On the z axis. Good. Now let's look at dilatation, which is also referred to as the volumetric strain. Dilatation, which is also referred to as the volumetric strain. Now let's consider a cuboid in the three principal axes, and the length on the y-axis is 1, on the z-axis is 1, and on the x-axis is 1. So we can say that the total volume is going to be 1 times 1 times 1, which is going to be 1. Therefore, if you want to get the volumetric strain, don't forget that we said that the strain is just the change in length over the original length. So therefore, in respect to volumetric strain, is going to be our change in volume. We are going to get a change in volume over the original volume. So from here, if we want to get the volumetric strain is represented with a symbol E, which is also called the dilatation. So from here, if you want to get the volumetric strain, then first of all, we need to get a change in volume over the original volume. So looking at this structure, if there is a change in volume, then the new volume is going to be at this side on the y-axis. The new volume is going to be on the x-axis. The new volume or the change, the final volume is going to be 1 plus the change in volume, which is epsilon x. And in the y-axis, the final volume is going to be 1 plus epsilon x. And on the z-axis also, the change in volume or the final volume is going to be epsilon x. So this is going to be the final volume. The final volume. And if the stresses are causing this material to deform or to contract, then we can say that the volumetric strain will be equal to the initial volume, which is VO, minus the final volume, which you can refer to as VF, all over the initial volume, which is VO. So from here, if we want to get VO minus VF, we know that the initial volume, the VO, was 1. So we have 1 minus our final volume. So our final volume is going to be the distance on the x multiplied by the distance on the y plus the distance on the z, the distance on the z, all over 1, all over 1. And from here, when we try to simplify this side, assuming that the strain is very small, then we can say that even if you simplify just the first two terms, the 1 plus epsilon x, 1 plus epsilon x into bracket 1 plus epsilon y. From here, we are going to get 1 times 1, which is 1 plus 1 times epsilon y is epsilon y. Epsilon x times 1 is going to give us epsilon x. And then we have epsilon x times epsilon y. So we are going to get epsilon x, epsilon y. But we are saying that this strain, the value of these strains are very small. Therefore, epsilon x times epsilon y, because they are very small, their values can be neglected. So from here, we can say that the first two terms is giving us 1 plus epsilon y plus epsilon x. Then, when we multiply it by the last term, 1 plus epsilon z, then from here we are going to get 1 plus, when we do the expansion, we are going to get 1 plus epsilon z plus epsilon y plus epsilon y epsilon z plus epsilon x plus epsilon x epsilon z. And we are saying that the deformations are very small. Therefore, this epsilon x, epsilon y, epsilon z will go to, is negligible. Epsilon x, epsilon z is also negligible. So everything there is going to give us this expression here, which is 1 plus epsilon x plus epsilon y plus epsilon z. Then from here, when we just expand from the bracket, we are going to see that 1 minus 1 is going to give us 0. And then now our change in volume is going to be epsilon x epsilon x plus epsilon y plus epsilon z. Good. So because we said there is going to be compression, if the forces are compressing this, then the final volume is going to be smaller than the initial volume. If they are in tension, then the final volume is going to be higher than the initial volume. So the formula would have been like this, all over VO. So because we are saying that if it was reducing, then all this is going to be negative, negative. But don't worry, we are going to take the absolute value so that it will represent both the contraction and expansion. So from here, when we simplify, we are getting this, which will be our volumetric strain, which will be our volumetric strain or the dilatation. So from here, if you substitute the value of epsilon x, epsilon y, and epsilon z, as we did in the previous slide, we said that the strain in the x will be equal to the stress in the x over the modulus of elasticity into brackets minus the Poisson's ratio into bracket the stress in the y over the modulus of elasticity minus the stress in the z over the modulus of elasticity. So this one is the stress. Good. So from here, when we put this into this formula, and then we also put epsilon y, which has the value of the stress in the y over the modulus of elasticity minus then the Poisson's ratio times the stress in the x over the modulus of elasticity minus the Poisson's ratio times, this one is the stress, not the strain. So the stress in the z over the modulus of elasticity, or we substitute this epsilon x and epsilon y into this equation. Then when we simplify, you can see that even from the x side, we have, when you simplify and you bring all the, let me just clean this space and try to do some simplification. Good. So when we try to simplify and put all the stresses in the bracket, then we can say that here we can just get the stress x in this, the stress y, and then the stress z. We want to bring all the stresses out. So the stress z. Therefore, from here we are going to get, when you bring this stress out, you'll be left with 1 over E minus, when you bring this stress out, you'll be left with V over E. And when you bring this stress out, you also be left with minus V over E. So from here, we can say that whatever is there, when we put these stresses in the bracket, whatever is here, when we find the LCM, we are going to get E into bracket 1 minus 2V. 1 minus 2V. And that is the formula for the volumetric strain. When we have stresses in the x-axis, stresses in the y-axis, and stresses in the z-axis. And the volumetric strain is just the volume per unit length, and then it is also referred to as the dilatation. Now, let's take it that this whole cuboid, which we have on our screen, is subjected to a uniform hydrostatic pressure in all directions. When we talk about hydrostatic pressure, let's take it that this thing is immersed in water. Then the water is going to compress all the sides equally. So we are saying that hydrostatic pressure is equal. And we know that stress is equal to the force over the area. And this is the same as the pressure. This is the same as the pressure. So if we have uniform hydrostatic pressure at all the sides, then on the x-axis, we have P. On the y-axis, we have our pressure to be equal to P, and our z-axis, the pressure will be equal to P. It means that the stress S plus, we have P plus P plus T. So here we are going to get 3P. And with this, our formula is going to be 3P. Our formula is going to be 3P. Sorry for that. Our formula is going to be 3P into brackets 1 minus 2V all over A. And when we bring this P out, we have P negative P into brackets 1 minus 2V over A. And the whole of this, when you find the reciprocal of the whole of this, or we can say that the whole of this is equal to 1 over K. And this K is what we refer to as the bulk modulus. Therefore, from here, we can say that K, which is the bulk modulus, is equal to whatever is here, the reciprocal of whatever is here. And we are saying that the K is what we refer to as the bulk modulus. The bulk modulus. And what does this bulk modulus represent? The bulk modulus is the measure of the body's ability to withstand changes in volume when compressed at all sides. So a body's resistance to changes in volume when it is compressed at all sides is what we refer to as the bulk modulus. And it is given by the formula which is indicated on our screen. Formula which we have on our screen. So quickly, let's move on and then continue with. Yes, so this is what has already been explained. We said that the dilatation of the volumetric strain is a change in volume over the original volume. And it is given by the formula which we expressed there. But in this case, let's take it that we only have stress in only one direction. We have a body which have only stress in one, force applied in only one direction. Then in that case, our volumetric strain reduces to this formula. And from here, we know that the stress over the modulus of elasticity is equal to the strain. So it means that when a single force is applied, our volumetric strain can also be represented with this formula here, or this, when we only have forces in one of the axes. Good. Now let's move on to the next page. Yes, we have a question. A bar of circular cross section is loaded by a tensile force P equals 85 kilonewtons. The bar has length L equals 3.0 meter and diameter D equals 30 millimeters. It is made up of aluminium with modulus of elasticity E equals 70 GPa, gigapascal, and Poisson's ratio V equals 1/3. Calculate the elongation delta, the decrease in diameter, change in D, the increase in volume, change in V of the bar. Assume that the proportional limit of the material is not exceeded. So from here, to solve this problem, we have been asked to calculate the elongation delta. And we know that delta is equal to the strain in the x direction, or strain in any direction, is equal to the deformation in that direction over the original length. But in this question, we don't know the strain, but we know the original length. Therefore, it means that we need to get a way of, we don't know the deformation, we only know the original length, and we are asked to calculate the deformation, and we don't know the strain. So it means that we need to get a way to determine the strain. But we also know that the stress is related to the strain by this formula. Therefore means that if we can calculate the stress, then in the question we have been given the modulus of elasticity, we can be able to find our strain. And we have been given the force, and then we also have the diameter as 30. So it can help us to be able to calculate for the strain. And we can also get the, so let's quickly run through this, and after that we'll look at the other parts of the question, which is the change in diameter and the change in volume. Good. So let's quickly try to solve that question. Solution. So for this question, what we do is that, first of all, we said that the strain epsilon x is equal to the deformation in the x direction over the original length. And we are saying that we know the original length, but we have not been given the strain. Therefore, we cannot get a deformation. Therefore, we need to get a way of determining the strain. And the strain is related to the stress by this up to the proportional limit. And once you have been able to calculate this stress S, we have already been given the modulus of elasticity, so we can be able to calculate the strain. So from here, we can say that our stress in the x direction will be equal to the force in the x direction over the area. And what is the force? What is the stress? The force given is 85 kilonewtons. So 85 times 10 to the power 3 over the area. And because it's a cylindrical, our area is going to be 3.142 times the diameter, which is, we are given as 30 millimeters. So we change to meters, it will be 0.03 over 4. And from here, our stress in the x-axis is going to be 120 megapascal. Once we have been able to do that, we can get the strain. You know that the strain x will be equal to the stress x over the modulus of elasticity. And from here, we can get our strain in the x direction as we were given the stress. The stress is 120 mega. We have calculated that. Therefore, we are going to get 120 times 10 to the power 6 over the modulus of elasticity, which we were given in the question as 70 gigapascal. So 70 times 10 to the power 9. Then from here, we can say that our stress in the x-axis should be equal to 1.72 times 10 sorry for that. So times 10 to the power -3 meters. Then from there, we can calculate our deformation. The x is equal to, from this formula, x should be equal to the strain times the original length. And we're giving the original length to be 3. So we have 1.72 times 10 to the power -3 times the original length, which is 3. And from there, we are going to get our deformation as 5.15 times 10 to the power negative 3 meters. Then the next part of the question, we were asked to calculate the change in diameter. The change in diameter, in that case, we are talking about the lateral strain. The diameter is in the y-axis. So we are saying that the lateral strain is always equal to, because it's a cylindrical, to be in the change in diameter over the original diameter. In the question, we have been given the original diameter, and we are looking for the change in diameter. However, we don't have this lateral strain, but we can get the lateral strain from the Poisson's ratio. From the Poisson's ratio, V is equal to negative epsilon y over epsilon x. And from here, we can say that the strain in the y-axis is going to be the Poisson's ratio, which is 1/3 times 1.72 times 10 to the power negative 3. So from here, our strain in the y, which is the deformation in the y-axis, is going to be 5.73 times 10 to the power negative 4 millimeters. So from here, if we have gotten the strain in the y, then we can calculate our change in diameter. Our change in diameter will be equal to the strain in the y-axis times the original diameter. The negative will be there because the diameter is decreasing. Because the diameter is decreasing. But in our calculation, our subsequent calculations, we are not going to use the negative. The negative is just telling us that the diameter will be decreasing. So from here, we are going to get 5.73 times 10 to the power negative 4 times our original diameter, which is 0.03. And from there, our answer will be equal to 1.72 times 10 to the power negative 5. And the next part of the question, we're asked to calculate the change in volume. We know that the volumetric strain is also equal to the change in volume over the original volume. From the question, we know that this formula can also be expressed as the volumetric strain is equal to the stress over the modulus of elasticity. When force is applied in only one dimension, the formula is going to be 1 minus 2V all over. So this will be the volumetric strain. So putting it into this formula, the change in volume which we are looking for is going to be all this, which is the stress over E, which is the volumetric, which is the modulus of elasticity. The modulus of elasticity into bracket 1 minus 2V times the initial volume, which is BO. But in the question, we don't have the initial volume. However, we have been given the diameter, so we can get the radius, and we know that the formula for finding the volume is equal to pi r square h. So this will be the original volume. And from here, our pi is 3.142. Our pi is equal to 3.142 times the radius. The diameter was 30 millimeters. So our radius is going to be 50 millimeters, which will be 0.015 square times the height, or in this case, it is the length. And from here, our original volume is going to be 2.12 times 10 to the power negative 3 meters squared. And once you have gotten this volume, we know the Poisson's ratio we know the stress over the strain, and we know that the stress over the strain in the x-axis, the stress over the modulus of elasticity in the x-axis is equivalent to, let me clean this side so that I can quickly finish with that question, and we'll proceed from here. So from there, we can say that the stress in the x over the modulus of elasticity is the strain in the x-axis. So our change in V will be equal to the stress in the x-axis into bracket 1 minus 2V times the VO. This V is the Poisson's ratio, which we have as 1/3. So from there, I want you to put the value of epsilon x, which you have calculated here, and the Poisson's ratio, which is 1/3, and the volume which we have calculated in this formula, and get the change in V. So the change in V, you find the value of that. Good. So with this, we can be able to determine all these other quantities. And with this, we can say that we are done with volumetric strain, the Poisson's ratio, and the generalized Hooke law. So now let's go to strain energy. Let's move on to strain energy. Good. Sorry. Let us look at displacement of axial loaded springs. Axial loaded springs before we look at the strain energy. So axial loaded springs. If I have a spring, so this is my spring, and the force of P has been applied to the spring. So from springs, we know that the force applied P will be equal to Kx, where this X is the deformation, in the string here. The original length minus when the force is applied, now the new length will give us the value of our X, which is going to be our deformation. So from here, we can say that if this S is represented with delta, then we can say that P is equal to K delta. And from here, we can say that K is equal to K over delta, as we have here. And this is what we refer to as the Spring's constant. Then we have what we call the compliance of the spring. And the compliance of the spring is just the reciprocal of the spring constant. So the compliance F is equal to 1/K. And this 1/K is the reciprocal of this. So we are going to get delta over the force applied. This spring constants and this compliance is mostly referred to as stiffness. So the spring constants is referred to as the stiffness of the spring, and the compliance is mostly referred to as the flexibility of a spring. In structural analysis. And from these two formulas, we know that the deformation for axial loaded bars is EL over EA. So substituting this in place of delta for K, we can say that K will be equal to, we already have our P here over our delta, which is going to be PL over EA. And from this, we can get our formula to be this P will cancel this P, and then the reciprocal of this will give us what we have here. And therefore, we can also say that the flexibility, which is also called the compliance, is giving us L, will be the reciprocal of this, which will be L over A. So that is all about strings which are loaded with axial forces. From here, let us move to strain energy. Let's move to strain energy. Good. Let's move to strain energy. When a uniform rod, for example, this uniform rod which we have, is subjected to a load, a slowly increasing load. Let's take it that we apply a load here, and then we start increasing the load. We will find out that the force which is applied at this side, the force which is applied, will cause deformation to this rod. So this was the initial length, and because of the force which is applied, we are having some deformation there, which is equal to x. Which is equal to x. So if we take just a small portion of the rod, and we want to get the work done in deforming that small portion, the work done in deforming that small portion, then we know from our studies that the work done is equal to force times the distance moved in the direction of the force. So from here, if we are considering just a small distance, then we can say that the work done, which is u, is equal to p dx. Is equal to p dx. Therefore, if we want to consider the total bar and the total deformation, the total work done in deforming this whole bar, total work done in deforming this whole bar, then we are going to add all the small sections together to get the total work done. And for that matter, we can say that now the total work done in deforming the whole structure by an amount of delta, which is equal to an amount of delta, which we can replace with SL, which is the total deformation. Then we can say that the work done U will be equal to the integral, which is the summation of all the small sections of the force times the distance of the small distances. So because we are looking at the whole length of the material and the deformations associated with it, and we are saying that the deformation is from 0 to SL, so we can integrate from 0 to XL. And this will give us the total work done in deforming the structure or the material. The total work done in deforming the material. And this total work done in deforming the structure is what we refer to as the strain energy. It's what we refer to as the strain energy. What we refer to as the strain energy. Therefore, we can say that strain energy is the energy absorbed in deforming a material. Strain energy is the energy absorbed in deforming a material. Good. So for an elastic deformation, we know that we have already seen that for strength, the force is always equal to kx. up to the elastic region. Therefore, when we substitute this Ks in place of our force, then our total work done, U, capital U, is equal to Kx dx. And we are integrating from 0 to XL. The K is constant, therefore we can bring the K out and say that we are going to get K integral of X dx from 0 to XL. And from here, U is going to be equal to the integral of, in integration, we add 1 to the power. So this is raised to the power 1. So we have 1 plus 1. 1 plus 1 all over the 1 plus 1. So we are going to get x raised to the power 1 plus 1 over 1 plus 1. And from there, we are getting everything that x raised to the power 2 over 2. Our k is in front. Sorry, we are finished with the integration. Our k is outside, and from 0 to XL. From 0 to XL. So from here, we can say that the total energy is equal to half into bracket Ks squared. Ks squared. And if we substitute our XL, 0 will give us 0. So when we substitute the XL, it means that the total energy is going to be half into bracket P So we already know that from this Ks squared, P is equal to Kx. So when we expand whatever is here, we are getting half Kx times x. So this Ks will give us P. So we are going to get P half P x. And this is going to be our total strain energy, which is the work done in deforming the material. The work done in deforming the material. Good. And this strain energy is equivalent to the area under the stress strain curve. So when I draw a stress strain curve like this, the area under the stress strain curve will be equivalent to the strain energy, or the energy or the work done in deforming the material. So if this is our stress and this is our strain, then the area under the curve is going to represent our strain energy. Good. So from here, let's move on to, yes, so we are saying that up to the elastic limits, or at the elastic region, the total work done or the strain energy is equal to half P times Xi. And because we are dealing with the elastic region, we said that the elastic region is up to, we have a straight line portion, which is up to the proportional limit. So the straight line is up to the proportional limit. So the area under the curve is our strain energy. Is our strain energy. Good. Now let's go to strain energy density. Strain energy density. In order to eliminate the effect of size on the work done. We have already stated that the work done U, capital U, is equal to the integral of P dx. But in this formula, the size of the structure or the volume of the structure is still a factor in this equation. Therefore, in order for us to eliminate the effect of size, then we are going to divide everything there by the volume of the structure. And when you divide the strain energy by the volume, whatever is there becomes small u. It becomes small u, and it is referred to as the strain energy density. So the strain energy density will be equal to the integral of P over V dx. P over V dx. But we know that volume is equal to area times length. So if you substitute this in place of volume, our strain energy density is going to be the integral of P x over AL. But from this, we know that P over A is the stress. So we are going to get integral of the stress. And we know that the deformation over the original length is the strain. So whatever is here is going to give us, whatever is there, let me clean this multiplication. So whatever is there will be equivalent to the strain, which is delta, or the epsilon x, the epsilon x. So this will be our formula for the strain energy density when we want to eliminate the effect of size on the work done. So we can say that this is the work done per unit volume. Work done per unit volume. Now, let us look at plastic deformation of a body. So let's take it that I have my stress strain curve like this. So this is my strain, this is my stress. And we are saying that for a ductile material, the stress strain curve looks like this, and failure occur at this point. And we are saying that everything under this curve is the strain energy. The area under the curve is the strain energy. So with this strain energy, because at this point, the material would have deformed permanently, it means that when the force or the load is removed from the object, let's take it that even before it fails, let's come to this point, at the point of yielding. So at this point, so this will be the strain energy up to the point of yielding. So up to the point of yielding, there has been a plastic deformation. Therefore, if the load is removed from the object, we will not recover all the energy. We will only recover a small portion of the strain energy. So we can only recover this side of the strain energy. And this portion here cannot be recovered. Why? Because part of the energy which is used for deforming this body will be dissipated into heat. And so this part B cannot be recovered. So only a small portion of the energy can be recovered when there is plastic deformation. Good. Having explained that, now let's go to what we refer to as the modulus of toughness and the modulus of resilience. modulus of toughness, and modulus of resilience. Modulus of toughness and modulus of resilience. Good. So first of all, let's look at the modulus of resilience. When we talk about modulus of resilience, when I draw my stress strain diagram again, we said that the first part of our stress strain diagram is a straight line up to the proportional limit where it starts to be a curve. So let's take that this point here is the elastic region, and then the curve continues. The curve continues. So this is up to the elastic region. Therefore, the energy to deform the material up to the elastic limits. The energy required to deform the material up to the elastic limits is going to be our modulus of resilience. So this whole area, we are talking about the elastic region. Therefore, the area under the elastic region is going to give us the modulus of resilience, which we are saying that it is the energy required to, or the work done in deforming the material up to the elastic limit, or up to the yield stress, The work done in deforming the material up to the yield stress is referred to as the modulus of resilience. So from here, we can say that our strain energy is equal to, don't forget that you have already derived that it is going to be the stress times the strain. We have already derived this. And from here, we know that the stress is related up to the elastic region. The stress is related to the strain by this formula. So from here, we can say that the stress is equal to the modulus of elasticity times the strain. So from here, we can put it here and say that we have E epsilon, B epsilon. And from here, when we integrate with respect to epsilon, we have the epsilon. So it means that we are integrating with respect to this epsilon, which is the strain. So from here, we add 1 plus 1, already is raised to the power 1 plus 1 over 1 plus 1, which is the power. So from here, we are going to get everything to be equal to E epsilon square over 2. E epsilon square over 2. The integration sign will not be there. We are done integrating. So from there, if we decide to express, we don't need this strain. We need to express the work done in terms of the stress. So if we want to express the work done in terms of the stress, then we can take this stress out. We can take this strain out and replace it with the stress. But we know that the strain is equal to the stress over the modulus of elasticity. So it means that this is the strain squared. So it means that when we want to replace it with the stress over the modulus of elasticity, then everything which is there is going to be the modulus of elasticity times the strain there is squared. So we are going to get stress square over E square. And already we have our 2 there. And from here, one of this E will take away one of this E. And so our formula will now be the stress square over 2E, which is modulus of elasticity. And we know that this stress is up to the yield stress. So wherever we see this stress, we can put the yield stress. So we can say that the yield stress square over 2A. So this will be our formula for determining the strain energy up to the yield stress. And we are saying that the strain energy up to the yield stress is referred to as the modulus of resilience. The modulus of resilience, or the work done up to the yield point. The work done up to the yield point. Good. So now, what is this modulus of resilience which we are talking about? The modulus of resilience, which we are saying that it is the strain energy up to the yield point, is a measure of the maximum energy that can be absorbed per unit volume without creating a permanent deformation. Don't forget that we have already established the fact that up to up to the elastic limits, yes, so up to the proportional limit, the material starts to deform permanently. Therefore, we are saying that the modulus of resistance is a measure of the maximum energy that can be absorbed before creating a permanent distortion or deformation. Quickly, let's look at the modulus of toughness, and we look at strain energy for normal stresses, and then we can bring our discussion to a close. So let's look at modulus of toughness. We said that the modulus of resilience is up to the yield stress. However, now when we talk about the modulus of toughness, it is the strain energy or the energy absorbed before the amount of strain energy density the material can absorb before it fractures. It is the amount of strain energy density which a material can absorb before it fractures. So we see that our curve is like that, and this is the point of fracture. Therefore, the area under the curve up to that point is what we refer to as the modulus of toughness. And we are saying that to eliminate the size, we always refer to the energy density. So the energy density a material can absorb before it fractures or before it ruptures is what we refer to as the modulus of toughness. Good. So take note of the difference between modulus of toughness and modulus of resilience. Then from there, I think we can just look at the strain energy for axial loaded members. Good. So for a member which is loaded axially, like what I have on the screen, we have already established the fact that the strain energy in terms of the stress is equal to this formula, which we said that is the integral of the stress in the x direction square over 2a. So this is the strain energy. But from this formula, we know that the stress is equal to P over A, and the volume is A dx. So when we substitute the volume and then the stress into this formula here, we are going to, and we simplify, we are going to get this formula. And when you integrate this formula with respect to x, then we are going to get P square L over 2a. With respect to s, first of all, this is going to be x, And then we are integrating from 0 to L. So you just substitute the value of L here to get E square L over 2AE. So anytime you are given a rod with uniform cross section and you want to get the strain energy will be given by this formula. So quickly, let's solve an example on strain energy for normal stresses or for axial loads. And once we are done with the question, we bring our session today to a close. Good. So determine the strain energy and the strain energy density in the step rod. Sorry, we are only going to determine the strain energy. You can determine the strain energy density, but in this question, we are only going to determine the strain energy. In the steel rod assembly, AB is steel and BC is brass, and we have been given the stress up to the yield point at 250 for steel, and that of brass is this, and then the modulus of elasticity for steel and modulus of elasticity for brass. So just as we saw for deformations as a result of axial loads, also anytime you want to determine the strain energy with respect to changing diameter. Now you can see that the diameter changes from this point up to this point. And we know that the strain energy is related to the area. The strain energy is related to the force applied and the area and the modulus of elasticity. So it means that anywhere we see a new force, we need to divide into section. Anytime we encounter a new diameter, we need to divide into section. And anywhere we see a new material, we need to divide into section. Therefore, to solve this, first of all, we divide into section. So up to this point is going to be one section, and the whole of this is going to be another section. So if we take this section and we cut through here, then what is going to be the internal force? So this force is here. To every action, there is equal reaction. So we have the equal reaction here. And from here, we can write NBC. We can write NBC going to the right minus 20 going to the left is equal to 0. And we can get the force in that section. NBC. From there, NBC will be equal to 20. And when we come to this section and we cut also, we are going to get our forces in this distribution, and this will be our reaction. So we can write the equation. NBA is going to the right, so NAB minus 30 minus 30 minus 20 should be equal to 0. And from here, NAB should be equal to 80 kilonewtons. And you can see that that is what we have done in the next strain. And once you have been able to determine NBA, we put in the formula for determining the strain energy for axial loads, which we just derived. So we calculate the strain energy for this side and the strain energy for this side, and we put the two of them together. So we are going to get, let's say that this is U1, this is U2. So we are going to get the total to be U1 plus U2. And we are done solving the question. So that is what was done in our next page. So that was what was done here. I've already explained the first part. So we just calculate the area for the first section and the area for AB, and also the area for AB is pi r squared or pi d squared on 4. And we know that the diameter of the first portion is, we're told that diameter is 100 millimeters. So we change to meters, that will be 0.1 square. And then the diameter for rod BC was 75 millimeters. So when you change to meters, you get that, and we get the area for AB and area for BC. And now we put them into this formula, which we are saying that is the formula for finding the strain energy. So we have already calculated A and B. We know the length of AB. We then 2 times the area we know, and we are told that AB is made of steel. We also know the modulus of elasticity. So we put all of them there. And then we do the same for BC. We know the force in BC. We know the length of BC. We know the area. We know the modulus of elasticity for the brass. And then once we put them together and we sum them, we will get the strain energy for that side. But this formula is only valid when the stress is less than the yield stress. So I believe it is a simple problem which you can easily go through and understand. So this brings us to the end of our lecture on this session. Thank you for watching, and we are happy you kept in touch with us. To end here, kindly subscribe, like, share, and hit the notification bell. We'll come again and we'll see ourselves again next time. Until then, have a good day. Bye-bye.